Data Center Infrastructure Design for Aspiring Engineers. Hello, I am Sarah from Sanglesoft. Welcome to our course. Data centers are the backbone of the modern digital world, housing critical data and applications for businesses and organizations worldwide. The infrastructure of a data center is crucial to its reliability, efficiency, and security. A well-designed infrastructure ensures data is protected, services remain uninterrupted, and operations are optimized. In this lesson, we will look into data centers covering the following points. Definition of a data center. Type of data center. Main components of a data center. Standards of data center. Tier classification of data center. Design of data center. So what is a data center? A data center is a physical facility that hosts computer systems and their associated components to store, process, manage, and distribute large amounts of data. A standard data center comprises multiple networked computers, storage, computing infrastructure, and cooling systems. It can be a dedicated space within a building or an entire building complex. Type of data center. Enterprise data centers. These are built, owned, and operated by companies and are optimized for their end users. Most often, they are housed on the corporate campus. In this lesson, we mainly talk about enterprise data centers. Managed services data centers. These data centers are managed by a third party or a managed services provider on behalf of a company. The company leases the equipment and infrastructure instead of buying it. Colocation data centers. Colocation facilities are large data center facilities in which you can rent space to store your servers, racks, and other computing hardware. The colocation center typically provides security and support infrastructure such as cooling and network bandwidth. Cloud data centers. In this off-premises form of data center, data and applications are hosted by a cloud services provider such as Amazon Web Services, AWS, Microsoft Azure, or IBM Cloud or other public cloud provider. Edge data centers. Edge data centers, typically smaller than other data center types, help businesses facilitate data transfer requiring minimum delay. They are typically located near the end user. Edge data centers are used to process data in real time for IoT, 5G automation, and emergency applications, given their requirement for low latency communications. Raised floor or access floor is a system consisting of completely removable and interchangeable floor panels that are supported on adjustable pedestals or stringers or both to allow access to the area beneath. Raised access floors are useful for distribution of cooling air, power and data cabling, and mechanical piping. Cable pathways should be sized for the maximum number of cables expected with a 50% additional capacity to allow for future growth. If both power and telecommunications cabling are distributed from below the access floor, then the power cabling should be routed either adjacent to or within the cold aisle. The telecommunications cabling should be routed adjacent to or within the hot aisle. Grounding and bonding are important in data centers to ensure safety and reduce network problems and equipment failures. The goals of grounding and bonding are to minimize current flow and to carry noise induced by electromagnetic interference to ground. All metallic components in the data center should be bonded to the grounding system to minimize current flow and to send harmful currents away from the equipment. Vesta. Typically, data centers are protected with Vesta, which is simply an acronym for Very Early Smoke Detection Apparatus, is a smoke detection system that is constantly and actively sampling the air around it. Also known as an aspirating smoke detector or air sampling device, these systems detect even the smallest products of combustion and send out an alert as soon as these changes take place. Vesta systems are especially suited for protecting high-value assets. A Vesta system allows the fastest response to a possible fire condition because it is constantly drawing air from the room through sampling points along the piping. It will send an alert as soon as the smallest amount of smoke is detected, much faster than standard smoke detectors. Vesta systems are designed to overcome the difficult challenges presented by data centers. The definition for a clean agent as per NFPA 2001 is a volatile or gaseous fire extinguishant that is electrically non-conducting and does not leave a residue upon evaporation. The agent is kept in liquid form in pressurized cylinders. When smoke is detected, The solenoid valve opened to release the pressurized agent through the piping and nozzle network, which will change state to vapor due to its low boiling point, where it helps control the fire by absorbing heat from the space. The two most common types of clean agent used in data center protection are FM200 and Novec 1230. The main components of a clean agent system, FM200 or Novec system, is control panel, smoke detectors, solenoid valves, FM200 gas cylinders, sounders, flashers, manual pull stations, hold abort buttons, ventilation purge fans. According NFPA 75 and 76, fire protection sprinklers need to be provided in aisle containments, or the containment panels shall be open in the event of a fire. When using FM200, the minimum design concentration should be between 6.7% and 9% at the lowest anticipated room temperature. A data center power distribution system typically includes power distribution units, PDUs, uninterruptible power supplies, UPS, and circuit breakers. PDUs distribute power to multiple servers, while UPS systems provide backup power during outages. The system ensures availability and reliability by delivering power to all in-use IT equipment. A computer room air conditioning (GRAC) unit is a device that monitors and maintains the temperature, air distribution, and humidity in a data center, network, or server room. CRAC systems have better air filtration, better humidity control mechanisms, and higher airflow than typical AC systems. Security is paramount in data center design. Firewalls, encryption protocols, CCTV cameras, and access control measures ensure that sensitive data remains protected from unauthorized access. DCIM, Data Center Infrastructure Management, is a combination of software and various sensors to manage and optimize the performance of data center infrastructure. DCIM software helps the data center operators to monitor, measure, and manage the utilization and energy consumption of data center. Sensors include temperature and humidity sensors, water leakage sensors, airflow sensors, air pressure sensors, multifunctional power monitoring sensors, rack door read switches, etc. Network connectivity, providing high-speed data transfer. We will discuss data center networks in another session. Hotisle and Coldisle data center. Hotisle and Coldisle data center design involves lining up server racks in alternating rows with cold air intakes facing floor grill side and hot air exhausts facing the other. The rows composed of rack fronts are called cold aisles. Typically, cold air are reaching through raised floor plenum. The rows the heated exhausts pour into are called hot aisles. Typically, hot aisles face crack units, return air paths, or ducts. This CFD, Computational Fluid Dynamics simulation, shows the airflow path of a hot aisle and cold aisle data center. There are 4 primary standards supporting the design and operation of data centers. ANSI TA 9942C Telecommunications Infrastructure Standard for Data Centers. ANSI BUG 02 2024 Data Center Design and Implementation Best Practices. ISO IEC 118015 Information Technology Generic Cabling for Customer Premises, Part 5 Data Centers. Uptime Institute's Tier Classification Standard. Tier Classification of Data Centers, Tier 1. Tier 1 rated or Class F1 data center has no redundancy, having a single path for power and cooling and few, if any, redundant and backup components. It has an expected uptime of 99.671%, 28.8 hours of downtime annually. This system cannot be maintained while it is operating, and single points of failure are common in this system. Tier 2 rated or Class F2 data center has redundant path for power and cooling and some redundant and backup components. It has an expected uptime of 99.741%, 22 hours of downtime annually. N equals the minimum number of components required to run the data center environment, need. N plus 1 equals an environment where a single additional component is added to the number needed. Tier 3. A Tier 3 rated or Class F3 data center has multiple paths for power and cooling and systems in place to update and maintain it without taking it offline. It has an expected uptime of 99.98%, 1.6 hours of downtime annually, and is termed as concurrently maintainable. Tier 4. A Tier 4 rated or Class F4 data center has multiple paths for power and cooling, and a Tier 4 data center is fault tolerant, having 99.995% uptime. Sometimes referred to as the 4 nines, Tier 4 facilities have 99.99% availability, 26.3 minutes downtime annually, and often reach 100% uptime year after year due to their highly redundant power infrastructure. Space planning. The capacity of a data center is based on the size of the computer room space, floor space, or rack space available for IT and telecommunications equipment, and the capacity of the power and cooling systems per unit of computer room floor space. A balance between space and capacity needs to be determined at the outset when designing a new data center. Data center is to support and the number combination of those systems that are to be placed within each cabinet or rack. Space for power distribution, cooling system to be considered based the capacity of data center. Aisle containment systems. The effectiveness and efficiency of hot and cold aisle separation may be enhanced for air-cooled data center by a method known as containment. The objective of containment systems is to prevent mixing of hot exhaust air with cold intake air. This technique can substantially increase the efficiency of the cooling systems, improve the lifetime of the cooling equipment, and reduce energy costs. In aisle containment systems, the hot aisle or cold aisle is enclosed, usually with a semi-transparent, fire-resistant materials. There are two common types of aisle containment systems. Cold aisle containment systems. Cold aisle containment include containment panels, doors, ceiling panels, and containment strips. With these components and other accessories, we can design a cold aisle containment. Hot aisle containment systems. Hot aisle containment consists of a physical barrier that guides hot exhaust airflow back to the AC return. This CFD, Computational Fluid Dynamics Simulation Analysis, the airflow path of a cold aisle containment system. In cold aisle containment system, the cold aisle is fully enclosed. Cold aisle containment minimizes the amount of cold air needed by the IT equipments by confining the cold air to the space directly in front of the racks. Air from the hot aisle mixes with room air and is delivered to cooling units via open return paths. Using cold aisle containment prevents warm air from mixing with the cabinet inflow, producing a more consistent and cooler air supply, compared to a solution that does not use cold aisle containment. However, the temperature within the remainder of the room can exceed the allowed working temperature. This CFD, Computational Fluid Dynamics Simulation Analysis, the airflow path of a hot aisle containment system. In hot aisle containment system, the hot aisle is fully enclosed. The characteristics include cabinet-mounted ITE with front-to-rear airflow, i.e. cold intake air in the front and hot exhaust air in the rear, a ceiling over the hot aisle, the crack units that draw in hot air from the hot aisle and blow cold air into the cold aisle. Exhaust air returns to cooling units at high temperature, thereby optimizing efficiency of the cooling unit. Hot aisle containment is typically a more expensive solution since it requires a false ceiling. Here, the hot aisle containment prevents hot exhaust air from mixing with the air in the rest of the data hall. This results in lower average temperatures across the whole room, at the expense of a slightly less consistent air supply to the cabinets. Aspiring engineers seeking a career in data center infrastructure design and construction should possess the following skills: strong understanding of fundamentals, power, cooling, networking, familiarity with industry standards, TIA 942, BICSI, ASHRAE, proficiency in design tools, CAD, simulation software, project management and communication skills. The future of data center infrastructure involves virtualization and cloud computing, artificial intelligence and automation, renewable energy sources, edge computing, and distributed architectures. Data center infrastructure design is a challenging yet rewarding field that requires a combination of technical knowledge, practical experience, and a passion for innovation. Aspiring engineers can make significant contributions to the future of this critical infrastructure. Thanks for watching. See you in another session.